suppose I have a loop, and the loop looks like this. By the way, let us choose a coordinate system. Here's x, here's y. Or here's x. So here is the loop. It's 4 centimeters this way, and then it's 1 centimeter this way, and it's 1 centimeter here. So magnetic field. So there is magnetic field coming out, right? But is the magnetic field here the same as the magnetic field here?
No.
Are they equal in magnitude? The answer is no. Why? Which one is stronger, which one is weaker?
Stronger.
Weaker here. The farther away you get from the wire, it gets weaker. So you can't just say it's the magnetic field times the area. Okay? You have to integrate, because the magnetic field varies as you go along the x-axis. It's varying. The magnetic field is changing. So let's see what the what we can do. First of all, so here basically calculate the magnetic flux. Usually people put a subscript M to distinguish it from the electric flux. Okay, calculate the magnetic flux. So we know the following. Magnetic flux by definition would be B dot dA. But let's say dA points outside, and the magnetic field also points outside. So what's their dot product? 1. Or cosine of 90, cosine of 0 degrees, which is 1, right? They are parallel to each other. So it's it will just be, the dot product would simply be just B times dA. It would just be times B times dA. So it would be B times dA. Okay, that's the magnetic. Now what's the area? So first of all, notice the following. That let's say if I'm at here, if I'm at this point, right, versus this point, as long as I'm on this line, does the magnetic field change in magnitude? No, because all these points are the same distance from the wire, so the magnetic field is the same. So I'm going to choose a strip that is a length y, or 4 centimeters. Let me call this one y here. A length y by a length dx, by width dx. A length by width is dx. So the area dA will be the height here, which is y, times dx. That's the area dA. So, integral. We will worry about the magnetic field in a second. The area will just be y times dx. That is the area. The area of a small strip. Now what's the magnetic field at that point? Let's say when you're here. It will be it will be 1 centimeter plus it will be a distance x, right? It will be a distance x. Yeah, let's just say it's a distance x. So it will just be distance. So mu naught would be mu naught I divided by 2 pi times x. We normally say 2 pi r, but I'm using x. Now, where did this formula come from? Mu naught I over 2 pi x.
Oh, it's magnetic field.
For a long current carrying wire. Yes. Yeah. The distance x from the wire. Okay. That's the magnetic. So it's a formula we derived right in class a while ago. So okay, so we got that. So now we need to integrate. So mu naught is a constant, I is a constant, y is a constant, 2 pi is a constant. So the only thing that remains is the dx over x. So you have this. Mu naught times times I over 2 pi times y times the integral. Now we need to put the limits. I mean dx over x. What are the limits of integration? Well, it's from this to this. Yeah, from 1 centimeter to 2 centimeters, right? But we should be working in SI units. So 1 centimeter is 0.01 meters, and 2 centimeters is 0.02 meters. So now we can substitute. Mu naught is 4 pi times 10 to the minus 7 times the current. They said it's 1 ampere. The y is 4 centimeters, which is 0. Let's try it again. Scientific notation. 4 times 10 to the minus 2. That's y. Divided by 2 pi times 1 over x. The antiderivative is natural log. It will be natural log of 0.02 minus the natural log of 0.01, and the difference between natural logs will just be the quotient right here of their arguments. And 0.02 over 0.01 is 2. So this is just the natural log of 2. So you can cancel the 2 pi, so you have a 2. 2 times 4 is 8. This is 10 to the minus 9, so you have 8 times 10 to the minus 9 times the natural log of 2. So you end up with 8 times 10 to the minus 9 times the natural log of 2. I wait, somebody got it, just to double check.
Times 10 to the negative 9.
Yep. 5.5. Anybody remembers the units? They were Tesla meters squared or W meters. So that's the flux. All right. So now, Lenz's law. Okay, Lenz's law, and then we will. Lenz's law is qualitative. It tells you the direction of an induced current, and so we will discuss that. All right. I will need this board if somebody needs it. Please, yeah, I will
We put it down.
erase it in a moment. Yeah. Utilize this. So let me review a couple of things. I'm going to review a couple of things. So let's say I have a current loop. Right? So please pay attention. So you have a current loop, and let's say that loop of current. So here is the current loop. Suppose the current is running counterclockwise. Current runs counterclockwise. Everybody with me? Current is running counterclockwise. In what direction is the magnetic field produced by this current at the center of the loop? Coming up. Good. So you orient your finger with the current anywhere, and it's coming out. So that produces a magnetic field out of the board. Let's do this, the other one where you have the current going clockwise now.
Going in.
So I think you would say going in. Yeah, just orient your thumb with the current, and your fingers will be the direction of the magnetic field. Okay. So far so good? Alright, good. So here is the Lenz's law. Says this: if you have a changing magnetic field, it will induce a current, a changing magnetic field through a loop, through a current, through a wire, it will induce a magnetic field. So a changing, let me write it. B field will induce a current. If you have a loop. If you don't have a loop, obviously a change in magnetic field is not going to, there are no charges to create a current. You have to have an actual physical loop to create this current. And we would like to figure out in what direction that current will be. So the direction of the induced current produces or is such that it produces a magnetic field to oppose the change. It's a long expression. It's long, but in application it's not that bad. So my goal now is to show you, do a few examples to figure out the direction of this induced current. Okay? So there are really like four cases. And so all right. So we're going to consider, suppose we have a current loop. So example 1. Here's a current loop. Okay. Suppose there is a magnetic field. There's a magnetic field N. So if the magnetic field is uniform, is not changing, right? If the magnetic field is not changing, will there be a current induced?
No.
No, it says a changing magnetic field will induce this current. So if the magnetic field is not changing, then you don't have an induced current. Okay? Suppose now the magnetic field is changing. Okay? So it's changing. So in what direction, first of all, is the flux? Magnetic field is N, right? Is N. So suppose the magnetic field, suppose B is decreasing. Suppose the magnetic field is decreasing. So you have flux into the board, right? So if the magnetic flux is into the board, but the magnetic field is decreasing. So is the flux increasing or decreasing?
Decreasing.
The flux is decreasing because the magnetic field is decreasing. So you have to induce a current to oppose that change. So if it's decreasing, what do you want to do? Do you want it to decrease or no? Yeah, you don't want to decrease it. So you want to produce a magnetic field to slow down the change. So will you induce a current to the right or to the left?
To the left.
To the left meaning counterclockwise or clockwise. So let's see. Suppose it's counterclockwise. You think it's counterclockwise. So let's study that case. If the current runs counterclockwise, in what direction is the magnetic field produced? It's this way. So that will make the change even more. Will make you lose even more. You don't want that. So you want to induce actually a current that's clockwise. So let me say it again, maybe that will help. So please pay attention, okay? Initially, the magnetic field is not changing. So you have flux inside, right? So let's say you just have magnetic field going in. If the magnetic field starts to decrease, the flux is still going in, but it's not as much as before, right? You don't want that. You want the flux to remain the same. So you would like to produce a magnetic field inside, into the board, in order to keep the flux the same way. So now the question becomes, how do I produce a magnetic field into the board? Clockwise current. Yes.
Are you gonna produce a constant? Like, is flux gonna be constant, or is it gonna be?
No, it depends.
Yeah, it matters how much that's changed.
Yeah, yeah. We will quantify it in a little bit. It will be just a derivative of it. Alright? So, yeah.
What do you mean if you want to decrease or increase the magnetic field?
So the question says, just suppose.
So you want to stop making it decrease. You want to increase the magnetic field because it's decreasing.
Yes, since the magnetic field is decreasing, it means you're losing flux that's into the board. You're losing flux, you don't want that, so you need to produce some magnetic field into the board, and the question is, how do you produce it? So you have to run current clockwise. So in this case, if the magnetic field is decreasing, the current will go clockwise. So it always opposes the change, always opposes the change. We'll do 3 more examples. The next one will be exactly the same, but now let's think about this. So example 2. Alright, example 2. Magnetic field is in, right? Magnetic field is in what direction? In. But now suppose B is increasing. By the way, let me label this one. The current will be flat. So now, the magnetic field is what? Increasing. So the flux is into the board, right? The flux is into the board, but it's getting larger, right? It's into the board and getting larger. You don't want that. You always want to oppose. You just always want to oppose it. So it's going in and getting larger. So how do I oppose it? Well, I oppose it by producing some magnetic field out of the board to slow down that change, right? So I need to produce a magnetic field out of the board. So in what direction should the current run? Counterclockwise. Because if it runs counterclockwise, it will produce a magnetic field out, and that will help slow down the change. So in this case, it will be counterclockwise. Okay, 2 more examples. The first one is, the third one, the next 2 examples will be the magnetic field coming out. So here they are. Suppose now, example 3, and actually this one I will give you a chance to discuss it with the person, with your neighbor. So here is the magnetic field. It's coming out, right? Magnetic field is doing what?
Coming out.
Coming out. So there is a magnetic field that's coming out. And let's say it's coming out and increasing. So B is increasing in this case. So discuss it with somebody next to you, or think about it. And
Well, first of all, we're running the current. It doesn't just happen.
it happens.
Oh, it just happened?
Yes.
Oh, okay.
Yeah.
So you don't even have to put current?
You don't have to plug it. Yeah.
So like, let's say in this, why doesn't it completely stop in this type?
Why does
Drop
the magnet
magnet?
completely stop?
Yeah.
I will discuss that in a second.
I mean,
If the magnet doesn't move, is there a change in flux? No, so there will be no current to pull it, so you will start to fall. So Yeah, it wants to keep things the way they were.
Kind of like a stronger friction.
So if it didn't do that, then you just have
How what was
you just had like the current would just have be like increasing. You could just make a loop and you would have like an infinitely increasing magnetic field. It just doesn't practically make sense. At least that's
Okay, what's the conclusion for this one? The flux, okay, I heard clockwise. We have two, clockwise, okay. So the magnetic field is out of the board, and it's increasing. So you're getting some more. Well, you want to slow that down. So if you're getting too much out of the board, then it's getting, larger. You want to oppose. How do you oppose it? By producing your own magnetic field into the board. How do you produce a magnetic field into the board? You use clockwise. So clockwise. And the final case, I guess you will know the answer probably right away. It's the same one, but decreasing. Example 4. The magnetic field is out, but it's decreasing. Okay. It's out, so it's worth, don't just say it's the opposite of right now, but it's worth thinking about it. So it's out, but you're getting less. Well, you want to keep things the way they are. So if you're getting less, you want to produce some more in that same direction. So I need out of the board magnetic field. How do I produce out of the board magnetic field? This counterclockwise. So counter. Okay. Now to actually, I said, yeah, let's do one more question. Here's the question. Let's do one more. Yeah, I didn't get that one. So suppose you got the current this way, right? And you have a loop this way. It can be rectangular or circular, whatever. If you like, draw a circular loop. So here's the current. Suppose the current now is increasing. I'll give you a moment to maybe discuss it with your neighbor. So suppose the current is going up, but it's getting larger. So the question is, in what direction will the magnetic field run here? So think about it for a second.
Yes, so you're one now. It goes opposes as well.
So, In what direction is the magnetic field, first of all?
Into the,
The magnetic field is into, right? Your thumb this way, the magnetic field comes out here and then goes in. So the magnetic field is in. So if the magnetic field is in, the current is increasing, so a larger current will produce a larger magnetic field or smaller? Larger. So the magnetic field is in and getting larger. Well, you want to oppose that. So you need to run your current in such a way that you produce a magnetic field out, which is counterclockwise, right? Referring to this. So it's, yeah, it would be counter.
No, that's not what you said. No, that's not what you said. You said.
Yeah.
We're trying to justify that.
Yeah. So, you agree that a current that's running up will produce a magnetic field in, okay?
On that side of the.
On this side of the current or the wire. Yeah, good. So it's in. Now, as the current increases, what happens to the magnetic field? Does it increase or not? It gets stronger. So, good. So you got a magnetic field that's in, and it's even getting larger. You want to oppose that. So to oppose that, you need to produce a magnetic field that's in opposite direction. So that's out, right? So how do you produce a magnetic field out? You have to run a current counterclockwise or clockwise. And we have two pictures here. So it's the counterclockwise.
And you run the current through the loop itself?
Huh?
Would you run the current through the loop itself?
Yes.
Okay.
So the current through the loop will be induced. So the loop here, by the way, is not connected to a battery or anything. It will just have a current.
So if I'm looking at this in a tube, what am I seeing?
In a tube.
So like, is that?
You will have a current.
In the middle, like, is that I in the middle of it? It's like, you say I is increasing, but like,
Yeah.
the current through the tube is increasing?
I am not. You mean, this is a wire.
Yeah.
Yeah.
Oh, it's a Y, oh, okay.
Yeah, so the current in this wire is getting larger, yeah.
So, for example, you can connect like to that tube there. If you connect the wire, I mean like current.
Oh, we're not in the tube yet, so we will worry about that in a second.
Isn't this in a loop though? Isn't Lenz's law like talk about a loop?
Yeah, here's the loop.
It's like a magnet.
Oh.
The loop.
Oh,
Yeah. Okay, yeah.
Would the magnetic field on the other side of the current also be affected by that?
The magnetic field here?
Mhm.
Yeah, it will be coming out and getting larger, right? Yeah. But there is no loop here to experience that magnetic field, so there would be no current.
Would it be unbalanced, the magnetic field, as in there'd be like a higher magnetic field on the left side than on the right side?
Why wouldn't?
Well, because you blocked the right side.
Oh, I see, you're saying, in this particular spot here, because we're slightly decreasing it, yeah, yes. So the total magnetic field here would be the magnetic field due to the current, due to this current, minus the magnetic field that is induced here. So yeah. But we're usually just interested in the induced current. Okay. So, let's go to, we want, yeah, so let me erase the board and, go to the next question. So, so, suppose, now, here is what I want you to think. Here's a loop. Let's say the loop is on the plane of the board, and I have a magnet. Let's say this is the north pole of the magnet, right? Here's north. Well, let's pretend this is a magnet, right? This is the north pole. The north pole is here. And I'm coming closer. In what direction is the magnetic field? It goes like this, right? Yeah, so some of the loop magnetic field is going through the loop. So as I get closer, the magnetic field that goes through the loop is getting larger or smaller?
Larger,
Larger, yeah, because if I'm far away, how much magnetic field goes through the loop?
a little bit,
Very little. As I get closer, how much magnetic field will go through it?
a lot more.
More, yeah. So as I approach, is the magnetic field, well, first of all, the magnetic field is in, and it's getting
Stronger.
stronger. So what does this loop want to do?
Make a current, but
No, no,
this way.
To
no.
make current to oppose this increase, right? So it needs to produce a magnetic field out. So that means it will produce a magnetic field this way. So its own magnetic field will be this way. So you'll have a magnetic field coming out. So remember, the magnetic field is originating from here and then it loops. So this is the north pole of this loop. And this is the north pole of this magnet. So what does north do with north?
Repel.
Repel. Okay, so now we're ready to actually understand what's going on here. So you have your magnet here. I forget which one is the magnet. We can try it. That's the magnet. Okay, so suppose this is the north pole of the magnet, and it's falling. Now there isn't one loop. You can think of it as this one is many, many loops stacked on top of each other, right? Infinitely many loops, lots of loops. So as you approach each loop, what does the loop do? So this is the north pole of this one. The magnetic field is increasing, so it will set up its own magnetic field to oppose the change. So it will produce a current this way in order to counter the magnetic field. At any rate, if this is the north pole of this one approaching, there will be, each ring here will have its own north pole this way. So what does north do to north? It repels. And so it slows down the loop. Okay?
So,
Yeah.
if you turn the magnet to the opposite, the south pole,
Yeah.
does it going to be positive?
No, would be
That
exactly the
turns
same
to
way.
south pole.
Yeah. So, and by the way, when the magnet is in the middle, when it's in the middle, okay, came up. When it's in the middle, it's moving away from the top loop, but approaching this loop. So the top loop actually wants to attract the magnet because it's losing flux. And the bottom one, since the magnet is approaching it, it's gaining flux, so it will oppose it, but this one wants to attract it. So both of them will produce a force upward, so it slows down. Okay, so that's what's going on. Yeah.
If you like put the pipe horizontal and then you like try to push the magnet through, would it not move? Or would it still travel through?
The reason I don't do it, there is friction,
Oh,
right? It would be touching the pipe, so there would be an additional force. I don't want that one.
oh, because like when you have it down, there's also like gravity pulling the magnet down.
Yeah, gravity is pulling it down. So here's what you're saying, I think. Suppose we ignore friction, right? And you want to push it. Yeah, you will feel a drag force on you. As you push it, you will feel a force pushing you back.
Is there a way to make it go down faster?
Is there a way to make it go down faster?
So right now,
yeah.
following each other, so
Yes.
it can slow down, but
The way to make it go down faster, if you cut this pipe, make a little cut here. So what happens is, if I cut the loops, there will be, the current wants to loop, but then there will be no current. You will have just pluses here, let's say, and minuses here, or minuses here and pluses here, but you never have a loop, complete loop. So it will just pass by.
but that's the speed of falling down, right?
Yeah, it will just, at the gravity.
Is it possible to make it faster than falling down? Is it possible to make the velocity faster than just falling down?
The velocity.
So let's just
Oh, can I just, myself, push it?
like no,
Give it some initial speed?
Oh, okay, I will.
Is that what you're saying? It's hard, yeah, see, if I had a wider pipe, yeah, you can actually throw it. But with this one, it just barely fits, so it's tougher.
Doesn't matter how big the loop is compared to the magnet.
I mean, if it's too big and it's too far away, the magnetic field will be, small, so, yeah. Yeah,
Can you go over the north and south part again?
so what I'm saying is this. So think about just this loop. So here's north. I'm approaching. Magnetic field is into the board and increasing, right? So the loop will have to oppose it, will oppose that change. So it has to produce a magnetic field this way. So if something is producing a magnetic field this way, we can consider that the north pole of that thing. So this would be, its north pole is facing this way, and this north pole is facing it, and north with north repel.
So north is like the direction it's pointing, like away from, I guess.
Can you say it again?
Like the north direction is
Is where
like the same
magnetic-
direction as the
Yeah,
the
the magnetic field originates from north and then loops around and comes back. I'm trying to draw, so the magnetic field goes like this.
like around the
Yeah.
okay.
Yeah, just like the north and south here, or the loop, if the current is running this way, this would be the north.
Okay.
The other side would be the south.
Thank you.
Okay, so I want to, just at least introduce Faraday's law. Oh, you had a question? Oh, you did?
Oh yeah, I was
Yeah.
curious if the copper was like a perfect conductor, like electrons could just move freely through
Yeah.
it, and you drop the magnet, would it just hover in the middle?
Yeah, you can have yeah.
That's kind of like what a
Yeah.
solenoid does, right?
What is it?
Or maybe not a solenoid, but
Well, if you
or
ever,
some sort of thing. Like if you were after to like induce a current and threw it with like a battery or something, you
Yeah.
could get it to hover, right?
yeah, yes, it can hover, yeah. There are different demonstrations. There is one where if you lock the circuit, actually the loop just flies off all the way to the ceiling. Yeah, if I find it, I can send you an email. I don't know if we have it here or not, but anyways, let me introduce, Faraday's law, yeah.
Wait, so say you like plug in the tube to like the wall or something, and it creates a current. Would it like shoot it out or like make it go faster?
If I'm coming this way, if the loop is fixed, it cannot move, right?
Uh-huh.
But if the loop is not fixed, it is possible for the loop itself to move, yeah. Yeah. So, and if the change is sudden enough, the current will be large enough and the repulsion will be large enough for it to be propelled, yeah. So, how much magnetic field will it induce? That's what Faraday's law measures. So it says the following, this is a new law of physics. It's not a law that you can derive or anything. It comes from experiment. So you can motivate it, but you cannot say it comes from this. Just like Newton's law, you cannot derive them. It says, yes? Says the electric field dot ds over a closed loop. What was this before? The integral of the electric field over a closed loop. And how much was it over a closed loop?
Zero.
It was zero. It's a conservative field. The electrostatic field is a conservative field. Well, now we're going to edit that. It's no longer zero. It's going to be this. d dt